A very warm welcome to you all here for tonight's discussion, the link between classical reserving and granular reserving through Doublechain ladder and its extensions. But now, enough from the chair, and I'd like to invite Jens Nielson to present. So while Jens takes the stand, let me tell you a little about him. Jens has worked as an appointed actuary and led various product development departments before specializing in research and development. He became research director of RSA with responsibilities in life as well as non-life in 1999. From 2006 until 2012, he worked as an entrepreneur, and he is still co-owner and board member of the Copenhagen-based Science First and Fredensborg Advisor. He is co-author of over 100 scientific papers in reviewed journals of actuarial science, economics, econometrics, and statistics, and also one book on quantitative operational risk modeling. Jens is currently professor of actuarial science at Cass Business School at City University. And Jens, over to you.
Thank you very much. Is this working? Yeah, it's working. Thank you. First of all, say thank you very much to be allowed in these halls. I've never been here before. It's very impressive what you can have here in London. Yeah. Today we're gonna go forward in time to some extent, but we're also gonna go back in time. We're gonna talk about reserving, which is a good old topic for actuaries. We have talked about it forever, always. I mean, this is probably one of the most important things actuaries are doing when it comes to working in the daily office, and it's a big responsibility to get it right. I mean, we talk about continuous and aggregated chain reserving. I have it in the title, and I'm trying to make a point out of it. It's not so different. It's not that different. I mean, there's been quite a few actuarial meetings lately where some have advocated that we should go into continuous granular approaches towards modeling, and it doesn't work anymore when you have aggregated, discrete data because you lose information and things like that. But I have the argument that we're still doing the same thing. And it's not like it's a game changer to go into continuous thing. It's still the same challenges. So we're actually fooling ourselves if we think that we should start completely afresh and losing out on everything we know. We have to remember what we know. So this is why I'm trying to make the link today. So guess who this guy is? Who's ever actually tried to do a reserve? You know, a real one with a number on it, signing it off in the room? Who did a reserve themselves? A few. So the baby, that's the guys who actually did it, who's actually doing it. and they not so much talking about it, but actually doing it. And those people have a lot of knowledge. They're not terribly well articulated, to say the least. It's very hard to go to practical actuaries doing the research and get exactly all the wisdom out of them in a short conversation. It's not going to happen. Therefore, it's called tacit knowledge, what they possess many times practical actuaries. And it takes a while. You almost have to work with them for a while to learn their knowledge, right? And I think one has to do that to develop reserving. What you shouldn't do is to be the evil man here. You shouldn't just ignore all the knowledge out there and start developing all kinds of methods, ignoring the knowledge that's already there, although unarticulated. Because if you do that, you might lose out on the babies. You're going to throw the baby out with the bathwater, and you develop methods that's unrelated with the real issues. So now we go back to the discussion, aggregate or continuous. Is that really the issue? Is that really what we have to decide? Do we have to make a game changer from aggregate to continuous? So now ask anyone out there, what is this? Is this aggregate or continuous? I'm just plotted the data. I just plotted standard reserving data on a triangle that I think everyone has seen. Is this aggregate or is it continuous? It depends on the eyes. This is paid data. It looks like a histogram. What is a histogram? I mean, in certain parts of the literature, a histogram is a non-parametric estimator of some shape. So it's a continuous non-parametric estimator of something. However, we can also call it aggregated data because it's obviously discrete. So actually, it's both. It's aggregated and it's continuous. It's both. So it depends how you look at it. Histograms are, it actually turns out that the chain ladder is a projection of this aggregated data down on a multiplicative subspace. Sounds complicated. It just means that you take the closest multiplicative model to your paid data. You just take the closest, and then actually that is what chain ladder is. It's very simple. You have your data, you project it down, and you get a multiplicative one, and then you exactly get exactly the chain ladder everyone is using. So the point is, what if what we always had been doing with chain ladder, what if that's also important, even if we go into the granular data space? Maybe we could do the same thing there. So chain ladder is a structured histogram. We know from statistics, I mean, a histogram is a non-parametric estimator of something. We know from statistics that is almost the least efficient way of estimating non-parametrically anything. In the way statisticians talk, it would have a rate of convergence of n to the minus 1/3, which is the slowest rate of convergence you can ever have in non-parametric statistics. I mean, you can do better than histograms, but it's still an estimator. So what can you do? The simplest extension you could think of, sorry, histograms are not efficient. The simplest extension you could think of is kernel smoothing. That's a natural thing you would do if you go from actually working with histograms to be non-parametric, then people to be really continuous, but it also looks continuous. Then you go into kernel smoothing. So what have we done here? If you look at the graphs to the left, then you have a local linear unstructured density of something, but it's still on this triangle that you know. And on the right, what you have there is a projection down of the multiplicative space. So we're doing exactly the same as chain ladder, but now it's continuous. And down there we have used multiplicative bias correction, which is actually my first paper from 1994 was on multiplicative bias correction. So I have a special reason to put it in. But we know that histograms are not so efficient when you do non-parametric smoothing. But we also know that the worst shapes you could ever think of without bias correction is probably the shapes we're finding in reserving. So we should probably add some bias correction. I'm not going to talk too much about it, but we did it there. So you can do various estimators to the left, and then you can project it down. And actually, we are very, very close to chain ladder. We can keep tracking it back to chain ladder, what we're doing. So when you're projecting, what you can see on the right are 3 different projections. The dots is the chain ladder that you know. And the 2 other graphs are 2 versions of non-parametric kernel smoothers that are being projected down. They are, of course, very similar. One could also have smoothed the dots, just have been smoothing the dots. It would be called the method of sieves, but it's not so efficient, so that's not what we're doing. So what is chain ladder really modeling at the end of the day? They are modeling time effects. They're modeling the development effects. It's about time effects. They're modeling effects in the underwriting year direction and in the development direction. time effects. So we have to be careful when we go into granular stuff that we remember those time effects. Actually, many of the studies I've seen on granular data forgot about what we knew from chain ladder. So that's not what we expect. We expect that we add to what we already know, not just start doing something completely different. So my postulate is that the most important thing chain ladder is doing for us, that's time effects. And it would be surprising if the most important thing wouldn't be time effects, also when we go granular. That's what I expect. So remember your continuous chain ladder when going granular. I'm being a little bit manipulating here because we wrote a paper called Continuous Chain Ladder that's doing these things. So this is what we like to call it. So the warning when you're going granular, if you dig really deep into chain ladder, it's actually impressive how general chain ladder is. You can show that it's working under very, very general conditions. What you can also show is that if you try to build a very complex system out of many steps to get the same numbers, then you get bias for every single step you do. That's the underlying law of mathematical statistics. So one has to be careful when building very big systems, then one is not just adding systematic error and being more wrong than even the simplest things. So clearly, when we have all this data and this big data revolution and continuous data and everything, make sure that we're doing better and not worse than before, okay? So this is an introduction when we talked about the continuous against the aggregate, because sometimes when I'm giving the talks about double chain ladder, people came to me and said, oh, I think the granular data is more important. So I had to make this introduction just to make sure that, yeah, we still back to the aggregated data, but the insight we get from the aggregated data is also important when we do go granular. So this is actually what you should take away from this. So where would we go from here? I will tell you about double chain ladder, Ferguson, and the whole game. What I think is the important thing. Double chain ladder is reproducing chain ladder. It's a paper, me and Richard and Lola, Richard is sitting here, we had to do 3 papers before we got it. But finally in 2012, we were able to reproduce chain ladder from a system of 2 triangles where we actually got a proper statistical model exactly reproducing the numbers we get from chain ladder. And then we get a response, right? Why would you do that? Why would you spend so many people's time and your own time to just reproduce what we already have? We would do that because we do a proper mathematical model, statistical model leading to chain ladder, where we understand what's behind it, such that we know how to change it. The problem with chain ladder as we have it today is actually there's so much going on underneath it that people don't understand. And therefore, you cannot change it very well. And every day in the office, there are people sitting trying to change chain ladder that actually don't fully understand the underlying mechanism they're changing, behind that changing. The big game, I see for the near future is to understand how the different chain ladders play together and how to generalize them. Then we can generalize it to granular situations, and then we can even go from there. But then we can do it step by step from where we are today into the new world, and not the other way around, starting with the new world and then hope we get back to where we are today. Prior knowledge, when you work with incurred data, I call it prior knowledge. I don't call incurred data data. It's not data. It's made by people somehow in the office, so it's not data, it's expert knowledge or something like that, it's prior knowledge. And it cannot be treated like data. One cannot take incurred data and say, oh, here we have some data, and then we put in a model, and then we shuffle it around, and then we get bootstrap something, and then we have some numbers. I don't think one can do that. One has to take into account what it really is. And incurred data is an estimate made by people of the future. It's not data, it's something else. So the big thing is to how do you make paid data that is real data work together with incurred data that's not data on the same scale. I mean, I don't know how many of you have experienced that. I experienced that when I was working as a real actuary, so to speak, that there were discussions when the paid data and incurred data were giving the wrong number, the very different number. I mean, we were working with Swedish teeth at some point, and one of the two, my Danish version of RSA was broke, and one of the two that were not broke. Because Swedish teeth is something like you have a damage when you're 2 years old and it's only repaired when you're 15, and if you run a model, it's very, very uncertain what's going on. Incurred data was giving one answer, and paid data was giving another answer. And actually, the discussion we were having, one against the other, was not very intelligent. It was something like, I believe in incurred data, I believe in paid data, and then we were standing in front of each other. Right? And I'm sure probably most of people in the room have been part of such a discussion. Yeah. So the challenge is to get incurred data and paid data down in the same model, down on the same scale, so they can be compared on a valid way. In statistics, we would call it validation. How can you validate one against each other? We have been working on this, and we have a solution to that, but we're still only on the discrete moment. But the introduction should tell you it would be the same had we gone granular. Yeah. The way we have been working, well, we were working many years with RSA, and every year we did a paper. So it was practical and it was academic at the same time. So every year we hired 3 interns, put them into RSA, and they tried the method out whether it worked. They came back and told us it was not working, and then we changed it again and wrote another paper. So all the papers about chain data actually came about after initiatives from practitioners. It was not the other way around. It was the RSA employees telling us to change the method. And then we spent a year figuring out how to do that. And we did that for many years. And now we actually got quite far in the end. And they got published in actuarial journals, but also other places, operational risk. And just recently, we're starting to publish in mathematical statistical journals as well. Because it turns out reserving is a more general problem than just non-life insurance. It pops up in many places in statistics. I think every one of you know the claims reserving exercise, where accidents are coming in and you try to estimate IBNR and RBNS, and we have reporting and paid and so on. And we want to understand how big the claims are, the timing of them, the distribution of it. We want to understand the cash flow. So what is double-chain ladder? I'm not going to go into the formulas today. I know some of you probably going to get disappointed, but probably even more of you are not so disappointed. There are formulas in the papers, and there are also presentations from the gyro with the formulas in them. But today I'm just going to give you the highlights because we have so many methods now. But what is double-chain ladder? It's a statistical model that breaks down the classical chain ladder into its components. So you have 2 triangles, you have the counts and you have the paid. You run chain ladder twice, and then you do some mathematics on what you get, and then you get the whole system. So from running chain ladder twice, so the actuaries out there, they can do what they always did twice, and then they get a full mathematical statistical system of what they always did. When you have a full mathematical systems, everything becomes easy. You can easily do RBNS and IBNR. You just add them up because you have the full system. You don't get confused about bootstrapping. I know both Peter England and Richard is here, but there is some problems with the bootstrap we are using at the moment. But you don't have, if you have a full mathematical system of the underlying methodology, you don't have problems with the bootstrap. At the moment, we have problems with some of the numbers when we do the bootstrap from the insignificant numbers. If they're being shuffled into the significant numbers, we get crazy results. But this is because we don't have the underlying mechanism of it. If you have the underlying mechanism, you get sensible results even so. And you also get some knowledge of the tail, although we just recently realized that we still have some work to do this properly. So here you see the format are the two payment and accounts data. And one of the reasons we were working only with two triangles, it should be real data payment and it should be real data accounts. It should be really easy. I was not trying to say, come on, you should give us all our data. It was really easy, just accounts. But let me tell you one thing. I've tried this now with a few companies. It's very hard even to collect accounts data. Okay? I get all kinds of crazy versions of them that, of course, eventually lead to all kinds of crazy results. So we're talking about big data and all kinds of, Monte Carlo methods, Bayesian algorithms, complicated things. I mean, I'm talking about collecting accounts data. It goes wrong. I'm not going to tell you how many percentage of the time, but it's a double digit. Yeah. So it's important that we are careful when collecting our data, and even collecting this very simple extension of what we normally do is non-trivial and often go wrong. Okay. But this is the kind of data we need, and it should be, after all, within reach. I mean, it should be possible to do that. Here you see the system. So you have some counts with some parameters, some alphas and betas, and then you have some paid with some alphas and betas, and then you have a delay. And the parameters you're seeing here, then you have a mean. It could, some people would call it average cost per claim. So this is not very far from methods being used by actuaries already. And you can estimate the variance, and the variance can depend on you can see the gamma I is the severity inflation. The severity inflation in the underwriting year direction. It turns out when you actually look at good old chain ladder in this detail, it actually turns out that almost all the trouble we have with chain ladder is coming from the severity inflation, the gamma I up here, which is the inflation of the size of the claim in the underwriting year direction. That's actually what's causing many, many of our troubles. And this is also the reason why we're doing what we're doing. All kinds of things with Bernhofer-Ferguson and things like that, and improving and smoothing and things like that. It's not only the gamma that is the problem, it's the gamma for the last few years, just the most recent ones. That's the critical one. And we can identify it now because we can identify all these parameters. It turns out that you can make a much more complex system than this. This is a system we can identify and estimate and bootstrap and do everything. You can make a much more complicated system than this that we cannot identify and that we cannot estimate, but we can show that chain ladder is making sense under very, very general conditions. We can show that. We cannot identify all the parameters, but we can show if this very, very general complicated set of parameters was behind our model, then chain ladder was still giving the right mean. Then we could just not get the distribution because we cannot identify the parameters, but we can show the chain ladder is making sense. The only thing you cannot do with chain ladder almost is crossing. You cannot let it depend on I and j at the same time. As long as it's going in one direction only, all kinds of dependency, correlation, crazy things, the development one depending on development two, as long as it's only in one direction, everything's fine. Or in the other direction, everything's fine, but they cannot cross. So that's why if you go to a practical workshop, which I've done a few times, it's always something that is crossing that the actuaries take up as the problem. For example, calendar effects and things like that. It's always, it's when it's crossing, as long as it's going this direction or this direction, you can do very general things and chain ladder is still making sense. It's actually very hard to replicate if you should build the model from scratch. So chain ladder is quite clever in some sense. What you're seeing here is the severity inflation. What you will be presented for today are different methods having different severity inflations. And what you see here is that just the last few severity inflation, it turns out that the last few severity inflations are really key. So if you take a payment triangle, it's the same as talking about the last few numbers. I think most of you who have tried reserving would know that in this particular data set, we could do a chain ladder, and we would realize that 85% of the research are for the last few numbers. So it's really only a few numbers that's critical. So the major drawback of the classical chain ladder method is that the last 2-3 severity inflation numbers are volatile. So now really, I think it's quite some insight into a chain ladder model. We're still in the chain ladder model, but in the chain ladder model, you couldn't talk about it the way I'm talking about it now. You couldn't say it's the 2-3 last severity inflation numbers that's causing us troubles. We can say that now. And they're too unstable, and it's because of that we're doing all the stuff with the Bonhoeffer-Ferguson and stuff. So what is double chain ladder and Bonhoeffer-Ferguson? It was a paper, again, Richard, me, and Lola published as the first paper trying to show what one could do. Now one has double chain ladder. It's just one example. And now we are mixing not 2 triangles, but 3 triangles. Now we take the incurred data in, and we show that if we do what we normally do by running a chain ladder on incurred data, and if one is treating it as if it had been paid data, ignoring that it's not, then we make a definition of what incurred data might be. If it's unbiased and done perfectly well, then incurred data is actually estimating exactly the severity inflation, the same severity inflation as double chain ladder did. So we can by running double chain ladder on counts and incurred instead of running it on counts and paid, we get another version of the severity inflation, but this time from incurred data that's much more stable, if it's good incurred data, of course. Our assumption is that these claims estimates are exactly unbiased, conditional what we know, which we all know that's not always true, right? So I go back to the severity inflation here. So this severity inflation can be estimated from incurred data instead. And you will get the graph in a moment, and it actually looks more or less the same, except the last 3 numbers that are much lower. So the incurred data say you shouldn't pick up these last very heavy moments. And it turns out that the reserve in the end is going to be half as big if you do that. So now some people have said we cannot call that double chain ladder and Bonhoeffer-Ferguson because this is not what Bonhoeffer-Ferguson did. But I say, okay, I mean, I've read the Bonhoeffer-Ferguson paper. It's not very clear what's in it. I mean, it's not that you read it and then you know exactly what he meant, because he didn't have many models at the time. So I'm thinking more of the spirit of Bonhoeffer-Ferguson. What he wanted in his original paper, or they wanted in their original paper, was to get prior knowledge into the system and still making sense. And this is also what we're doing here. So that's why we called it that. It's a tribute to Bonhoeffer-Ferguson as trying to transfer their ideas into a modern setting. It's what we're trying to do, and that's why we called it that. It's by no means the only thing you can do to try to get prior knowledge in. You can also do other things. If you look at the incurred triangle and try to define what it is, you can also get the RBNSs out. The RBNSs you have in the reported but not settled numbers. it's a bit funny that we don't look on, actually when we do reserving, often we don't look too much on the RBNS. It's not sometimes we don't look at them at all. But I think it's a big decision if we do reserving that we change the RBNSs. If we do it, we should do it consciously. We should say we change the RBNSs from this to this. And it's because we think that the claim department is not knowing what they're doing. Clearly, we halved the RBNSs, so we did, added 30% to them or something. Because often RBNSs, there might be, 85% of the reserve. So one has to be, and that's the department doing it professionally, setting them. So if they're very, very wrong, and we're sitting in the reserving department, doing the numbers and get that the other department is 30% wrong, then at least one should have a conversation. So now you can do many things to Doublechain, and one thing you can do is do an RBNS preserving version of it. So what we basically say, now we put in as a condition that the RBNS in is RBNS out. The end result of the RBNSs are the one you started with. It's research being done by Munir, who's sitting here, and Caroline, my two PhD students. They're working on this stuff at the moment. And that can be done. And the way you do it is you throw the RBNSs in, you think of it, and then you forward the RBNSs into the future as a cash flow, and then you re-estimate again, and then you do an iterative algorithm. And at the end of the day, you get something looking like a chain ladder, or looking like a double chain ladder. But this time, the end result gives you exactly the RBNSs you started with, taking the information from the RBNSs, and you get a different IBNR because you get different parameters around. So this is probably the reserve you should take if you trust your RBNSs. If you don't trust them, probably it should be articulated that you don't trust them. And that's just one version. That's what we call the PDCL. It's not fully finished yet, because we don't think we have found the full potential of that idea. So, Bernhover-Ferguson, double-chain ladder, Bernhover-Ferguson, RBSA preserving double-chain ladder. That's one more method I will talk about today. And it's all about now getting prior knowledge into the system, right? Incurred data into the system. RBNS into the system. Of course, we should also have IDCL, incurred double-chain ladder, which is the double-chain ladder that is exactly producing the numbers you have for incurred data at the moment. So we also have that one. I'll go to that one quickly. This one. So what does IDCL do? It runs the classical chain ladder that everyone is doing at the moment, get some numbers, rephrase the severity inflation. Remember, it's really the severity inflation. That's where everything's going on. Rephrase the severity inflation into exactly that one, reproducing the incurred data, the incurred reserve. Why would you do that? You say, why would you do a double-chain ladder reproducing paid? Why would you do a double-chain ladder reproducing incurred? Because now we have a model of paid, we have a model of incurred, and we, by the way, also have a model of RBNS preserving chain ladder, and we have a model of a new one we did ourselves called Bernhover-Ferguson. So we have 4 different versions of chain ladder, but they're all defined as a proper statistical model. And what can we do then? We can compare them. And it sounds, yeah, of course you can do that. But hey, it's not been possible before. It's not possible to validate even the 2 methods most often used in the office. But with this method, it is. I think I have said this, that PDCL preserves the RBNS case estimates and so on. And the DCL parameters are adjusted accordingly. I will say that this is the direction of the research. And PDCL is preserving RBNS. What we are discussing at the moment is whether you can, by validating back in time, get a model for underestimation or overestimation of RBNS. Maybe there's a trend of the RBNS. You often see that there's been some overestimation, more often an underestimation in the past. And and the company is catching up, but it's not catching up in one go. They're catching up kind of over time. You can, and the next step probably is to develop a model that can catch that up, can get a trend of where the RBNSs are going. That should be possible, but it's not existing at the moment. And then you can, of course, bootstrap it and so on and so on. So that's what I just said. Validation is now possible. So you have all these methods, and they can be compared because they're defined on the same scale. So you can just cut off diagonals and validate. It's the same way as you're doing validation today. The problem is that if you validate incurred and you validate paid today, then the numbers you're getting are not comparable. So you cannot choose between them from doing that. Yeah. Now, what I want to show you here is a new software package that we are happy with, because it's a company that are using cash consultants. So this is a little bit like an advertisement for we have such a thing at Cash Business School called Cash Consulting, and they use Cash Consulting and produced. They have a software package already, but now they introduced all these methods in the software package. So I'm paying a little bit back to them from actually working with us. The package is called Ristimator, and it's doing all this stuff that I just told you, so you can get the numbers. It's a little bit better designed than our own package. We have a free R package doing the same things that you can just get on the net. But if you do Ristimator, then you get tables out of this, and you get all the numbers, the alphas, the betas, the delay. You get all the tables out here. And you can get the usual things, of course, like the curves you can see of the development in the different in the accident year directions and stuff like that. What you would expect. You can get the BDCL. And you can get the same for the BDCL. And then of course you can look at the different methods with the severity inflation. What you're seeing there is IDCL, BDCL, and DCL. So it's 3 different methods, but the only thing that make them different is the severity inflation. And here you can see the blue one is the BDCL. The paid one is the green one that's jumping up at the end because it's too volatile. The red one is quite volatile because it's man-made, right? It's the man-made incurred. And what we tried quite a few data sets with, say maybe 40 data sets or something over the last few years. And it turns out that sometimes incurred is doing incredibly well, much better than paid, because paid is too volatile. Almost as often, paid is doing much better than incurred. So it happens as well. But almost always, BDCL, as you can see, the blue one, is almost always doing sensible, whereas the 2 of them, paid and incurred, are maybe 1 out of 4 times completely off. So it looks like BDCL is stabilizing things, and it is a good compromise choice, so to speak. Here's just an illustration that you can split using DCL in RBNS and IBNR, so you can discuss those numbers. So you have your chain ladder, but it's divided in RBNS and IBNR, and you can discuss it. And that goes with everything we do with double chain ladder. All the models done with double chain ladder, you can do things like that. You can validate them, you can split them, you get a tail. Yeah. You can bootstrap them. It's trivial because you have a model and you can just run the model. There's no discussion. And then you get, these graphs that you know. So let me just mention the validation. You can see an example of a validation. So the green one you see here is that you cut off something. You cut off the most recent years. Now it's not clear how you should do a validation, because you could do calendar time. It could be the particular boxes. It could be the year, or it could be the total cut-off reserve you could validate through. It depends a little bit what you're after. If you want a very nice cash flow with details, then you take every single number you predict, or you can also predict the entire future. So there are different measures of prediction, and it gives sometimes different answers. And here's an example of a validation where you have to the left the double chain ladder, the BDCL, and the IDCL. And in this particular case, it's actually not on the same scale, but if it had been on the same scale, then in this particular case, BDCL is doing better than the two others. But what we often see is that BDCL is in the middle, and one of the two others is off. Yeah. But you get this kind of numbers, which is basically just the numbers. How wrong is chain ladder when it's paid? How wrong is chain ladder when it's incurred? And how does it compare to more advanced inventions within double chain ladder? And you can compare all these things and get numbers for it. And you can also build a routine and build some experience. And I think I'm so excited to get some challenging questions. So maybe I will stop. Yeah. So.
Thank you. Thank you, Jens. So the baton's passing to the audience. We do have a microphone coming round. So we're looking forward to an interesting and stimulating debate, and would like to encourage as many members as possible to contribute, if you would like to. If there are not enough of those who would like to, then we might pick on some who don't. The meeting's being recorded for publication in the British Actuarial Journal, so please clearly state your name before making your contribution, and wait for the mic to come past before you do either of those. And make sure you speak into the microphone. I think I wasn't at the beginning, so apologies for that. But now we are warned. So may we have our first contribution from the floor?
Hi, my name's Nora Shola. I suppose when I do a lot of my reserving, I do use the Bornhetter-Ferguson, and with that there comes a prior estimate of the ultimates that are used. I suppose in this sense, the way that you could introduce that is a prior estimate of claim counts, but I wouldn't know what that is, and I don't think many people would.
I think in some sense, when you see the IDCL, all it's doing, IDCL, if you run the incurred, then you get some version of the ultimate claims. And those ultimate claims is being translated into a severity inflation. So if you're running your Bornhetter-Ferguson, one could reinterpret them as one in severity inflation. One could do exactly the same as with IDCL, with your Bornhetter-Ferguson method, actually no matter which one you're using. So one could take what you're using and turn it into a severity inflation, and then we could put it up here and compare them on the same scale. So,
okay, but say if we're relatively new on a diagonal, for example, and we've only had 3 claims to date, and the projection is showing another 14 to ultimate. But in the past, you've seen 50 claims, 60 claims come through. Would you take 50 or 60, or would you take the 14, which is going to come through from your using the pure chain ladder on the claim counts?
I'm afraid it went a bit fast for me, all this. I probably, what I would do, is this sounds like something that you only have very recent information, and we do similar things as only take the last few years of information and run forward. We do that here as well, but I'm not sure. What you're telling me is that you're doing real handmade Bornhetter-Ferguson type of projection because you don't have much real data information yet. And I guess in that case, probably that's what you have to do. I'm not sure this is going to help you much. Yeah.
My name's Jeremy Law. I have a question. So this model, it is slightly more complicated than the chain ladder, and you're introducing slightly more parameters than just the normal chain ladder. Do you have any concerns about over-parameterization or the amounts of data you need, or the size of the triangle to make this work?
I think it works. I mean, there are different versions of size of data. What is not size of data is the number of numbers we see. That's not the data. The data is the underlying data. So then so how many data is behind all this? That's what the data is about. Sometimes when we talk about chain ladder, we mention the numbers in the amount of numbers in our triangles and say that's our data. It's not. It's what's behind it. If you have a lot of claims behind your triangle, then it's more stable. I'm beginning to think that going, then there's another direction. You can go from yearly data to monthly data to weekly data. And I'm beginning to think that if one is beginning to develop proper smoothing methods and so on and so forth, then one can actually work with even weekly data, even daily data, and do pretty much the same as we're always doing in chain ladder. So, and how much data you need? I mean, when we develop a bit further, then what mathematical statistics is doing for you, it's smooth more when you have less data. So where we should be going is that we actually the method automatically adapt to the amount of data. So I actually I'm pretty sure that you can get decent results even with small data sets. But of course it's better to have big data sets. I mean, that's clear. I don't know if that's an answer.
Thank you.
Hi. You mentioned that you had quite a large...
Sorry, could I just ask you to mention your name again, because we didn't pick it up last time because mine wasn't working so well.
That's fine.
Thanks.
I'm Bharat Raj. You mentioned earlier that you had a large number of data sets in your work in this analysis. Do you think maybe you could sort of give us a high level as to which lines of business you looked at, what sort of business this worked particularly well for, and which businesses you think this approach might provide data requirement?
Yeah. I don't have that data because it's all proprietary data. So I actually never had my fingers on them. The work was done in RSA. RSA people working on their own data and them showing me their results. That did all kinds of things. That did motor business with short developments, but there was a bias towards doing personal accidents and workers' compensation and the tricky ones, where they were interested in answers. Or there was also a bias towards doing tricky data sets where there has been some calendar effects in the middle of it. So there was a bias of them giving me the more challenging ones. But we also did simpler ones. Often we got, of course, more or less similar results to what they were getting already, because our methods are, at the end of the day, not too different from what they're doing already. However, we get a deeper insight into the results they already are having, and maybe a better way of communicating and talking about changing them. One thing that we were discovering that was very interesting when we were running so many data sets, it was if you saw this severity inflation I had, there was a tendency that the paid was jumping up, and then you had the burden of Ferguson that was very stable. In the beginning we said it's clear because it's very stable and paid is jumping up. But then when we saw the same happening for 25 out of 40 data sets, they say it might not just be accidentally. And this has led us into a new stream of research on what actuaries call operational time. Because it's probably this jump, not only volatility, but also partly because there's a change over time in the speed of reporting and payment and things like that. And that's the kind of thing you see from running it on many, many data sets. If you see the same pattern across data sets, then you get an idea to how to improve the method. Yeah. So that's what we learn from it. But again, every time we learn, then we run it again, and then we learn again. So it's probably never ending. Yeah.
Well, one of my own then. You mentioned Jens earlier that this is not just a non-life insurance problem. You're finding it other avenues to apply it to. Could you tell us a bit about that?
I mean, my own background was that I took my PhD in biostatistics at UC Berkeley in 1988, and what were you working on in San Francisco in 1988? If you did biostatistics and were specialized in survival analysis, you worked on the AIDS epidemic. And if you look at the AIDS epidemic, then it's quite clear that the structure of the problem is the same as the structure of reserving. It's the same problem. And actually, there's many forecasting problems that are the same in biostatistics as in reserving. And now come the interesting thing. It is maybe actuaries have something to offer to the literature here. Because in biostatistics, they have done a lot of papers. Someone did some method, someone did another method, a little bit like we see it in reserving. But there has never been like a massive amount of people doing it every day, like we've seen actuaries doing it and building up that kind of experience. And then I was talking to some statisticians. I have still connections to quite good statisticians from those Berkeley days. And then I went to them with this problem and said, this is not just an insurance problem, this is a general statistical problem. And look at the structure. This structure is fantastic. Let me show you why they got interested. If we go back to the beginning. So for them, when I talk to statisticians, this thing about taking a smooth estimate and project it down on a multiplicative space and then getting it, you think it sounds technical. For them, it's too trivial. They wouldn't write about that because it's so easy, right? So to motivate them, I said, there is something very, very special about this reserving problem. It is that everything you estimate inside the triangle, I mean, when you do a forecast in reserving, everything you estimate it from data. You estimate it from past data. You're not forecasting parameters. It's a very special, it's almost in between forecasting and goodness of fit. It's an in-between method that is much more stable and much more reliable than if you were forecasting. You remember, you have seen a number of longevity models that can run crazy in all kinds of directions because you're doing many things at the same time. That's real forecasting. That's difficult, and that can go anywhere. On the other hand, we cannot do goodness of fit only, because that's the past. But the reserving problem is so special that it's a particular structure where you can forecast without extrapolation. For some reason, it's never been published in statistics. So I went to them and said, okay, we call this in-sample forecasting, and then we publish it. And it just came out in Annals of Statistics, which is the most technical mathematical statistical journal in the world. And they did this stuff, and it came out, and they liked it. So, and I have big expectations that such a cooperation with people, some of the top kind of statisticians, mathematicians in this field, that it can actually give us something back to reserving again, having that kind of cooperation. So that's. I hope it goes both ways. They're learning from us, we're learning from them, hopefully. Yeah.
Thank you, Bharat. Thank you. questions? Martin.
I've just been jotting things down as the session's been going on. A few observations from practical experience from looking at different portfolios. Your initial comments about outstanding claims and therefore incurred data not really being data do make great sense to me. What I always do when looking at a liability portfolio is to graph the cumulative paids and then to compare the relative shape of those developments from one underwriting year to another. Then I do the same thing with the incurreds. Then I compare the two pictures and see how stable the development patterns are and which looks more plausible, the paid or the incurred from year to year. And that's from underwriting year to underwriting year. What I tend to see is that companies lean more towards believing the story that the incurred data is telling than believing the story that the paid data is telling. Whereas the paid data, in terms of consistency of development shapes, tends, I find, more often than not, to look much more consistent and way more persuasive. I've spent some time wondering why this is, and my feeling as to the likely explanation is that the paid data responds more quickly to changes in ultimate claim costs. I think the case reserving process, even assuming it's done in an unbiased way as possible, is a lagging indicator. And a good example there is the recent experience of the UK motor market. Now, quite separately, I'd also support the idea that you mentioned just now. The kind of work that we do in non-life reserving can be useful elsewhere. For example, I've been talking to a company that sells a service, but that sales process has many elements to it that unfold over time. First, you've got to persuade the customer to install your product, and doing that involves overcoming all sorts of hurdles. Then once the product is installed, you make money each time the product is used. So it's a simple enough problem, but the actuarial approach is to divide the thing into stages, measure them, and try and make sense of them in the way that's quite simple once you've explained it, but it comes more naturally to us. Thanks.
You were so friendly, Martin, to send me on email parts of what you were saying before, and I've been thinking about it, and I think I don't fully understand. I mean, I agree with this thing that paid has this ability to pick up things immediately because when things are happening. But it's very interesting that it's even more stable, and I would like to understand that better. So I hope you will take a conversation with me about it. But what I would like to see is, what I do believe is, if what you're saying is true, which we should investigate, or in the sense that if you...
I'm happy to explain it in general terms. I can draw that. There's this issue about confidentiality of data, but what I've described is dramatic and really persuasive sometimes. Yeah.
It's very interesting, and hopefully it can be incorporated in Doublechain data as well, if it's really true, because Doublechain data is still lacking visual methods, bringing better understanding into the whole thing, and that might be one option, hopefully. Yeah.
So another method.
Could you tell us your name, please? Thanks.
Jeremy Law.
Thanks.
Another method I've come across which attempts to combine or make use of both paid and incurred data is the Munich chain ladder. Do you have an opinion on this method?
I mean, I studied Munich chain ladder. I don't really understand it. My first ever published paper was on something similar. It was in the early days when you did prediction of AIDS. Then what people did in the very early days, they did a regression, giving your current status in the blood. So they run a linear regression, and then they did predict into the future, onset of AIDS, because they didn't have any data. And then said, now we take this data and say it's data, and then they predicted the epidemic and got numbers. And we showed in our paper that got out in Biometrica that there exists no probability space where this makes sense. Okay? It's not I mean, it was my first paper, and you shouldn't make a career out of writing papers like that because it doesn't gonna give you any friends, right? But when I read unit chain ladder, I mean, I'm not sure that I can. So I didn't write the paper, and but I had the same feeling from reading it, that when we are throwing some linear regression around, and no one really checked whether this makes sense.
David Wilkie. I'm not an expert on reserving and anything, but I have had some experience in analyzing different sorts of data. And you're mentioning forecasting of mortality rates. Well, that's obviously a triangulation sort of problem. You know for the underwriting year starting 100 years ago, you've got an awful lot of data. For the underwriting year starting last year, you've got very little data. If you think of year of birth instead of underwriting year, you've got a very good, you're just counting counts, you've a very good development for year after year is very similar, so that the chain ladder structure is taken over rather differently by the mortality rates. It essentially is doing the same thing. You're smoothing along by age from underwriting year and then trying to project the change in the chain ladder structure over the future. And that, as you say, is very difficult when you're trying to forecast a very different sort of problem. But the numbers are usually very sufficiently large with population or even assured or lives or pensioners data. The numbers are big, so there aren't problems, and the amounts data doesn't come into it terribly much. On the other hand, the other bit of a little bit of experience in is the very large claims in shipping liability insurance, where the numbers are tiny in comparison, and the amounts are huge. And the distribution of amounts becomes critical. And whether one's doing it by paid or by estimation, the numbers of cases are not enough to try to estimate the future from terribly well, from smoothing the paids and so on, because each case is very different. I mean, to mention names, the estimated costs of Costa Concordia were clearly depended on quite a lot of different elements. There were some injuries, there were some deaths, there was some damage, and there was an absolutely enormous salvage costs. And the only people that could do some estimate of that were the individual estimators, engineers and shipping people, knowing how much the salvage would cost. No actuary, no statistical methods is going to help there. The cost of Hoeg Osaka, very recent in damage, I have no idea what the costs might be. They might not even be terribly big. The costs of another ship that I've heard about, the Rena, that was wrecked on a coral reef off New Zealand, which is also sacred to the Maoris. The problem there is whether you need to do something about it. The costs of salvage would be enormous, but is it how much is it necessary to do to preserve the coral and to satisfy the feelings of those for whom there's a religious element in it too? And that comes into Costa Concordia. It was not possible to take it out to sea and dump it because there were bodies in it. And they had to be rescued. Yeah. And in a Catholic country like Italy, dumping the bodies wouldn't have done. So, and you don't know whether these things are going to, the binary problems very often, similar problems with tobacco liability. Which way is the court going to go, one way or another? And I think with very big claims, I would think you need to rely more on the individual estimates from experts and recognize that where there's a court case involved or something like that, it could go either way. You have a binary problem to deal with. I always feel that the chain ladder system works nicely when you've got very large numbers of cases, as in motor claims. Motor claims are generally not running into hundreds of millions. You know that. Shipping claims are. So would earthquake or other things like that.
David, I agree with both points. I mean, I would like to, clearly the longevity problem is the same problem. In my world, it's the same problem. It's just two different histories. So when you look at the reserving literature, it looks completely different from longevity literature. It's not because the problems are different. It's just so happened. Different schools, different network, different tradition. Accidentally look different, but it's the same problem. What I would like to see, what I think longevity, it's not a triangle in longevity, it's a parallelogram. It looks slightly different. And we actually did one more in our recent in-sample forecasting paper coming out in IME, we also did a longevity version of it, so that it does exist. What I would like to see in longevity is that we do the middle step. It's not like I'm against doing forecasts with time series where you have Licata kind of time series forecasting, but I would like to see the forecast without the time series because it's confusing me. It's so many numbers and it's so volatile. So I would like to do it stepwise. Do what corresponds to the reserve first. Do the numbers first before having all these time series, because I don't really. It doesn't really do much for my intuition, these time series. What's going on with the trends, with the long-term trends? So doing the long-term trends first, and then add the volatility afterwards, like we do in reserving. I think longevity could become more understandable, more intuitive from such an approach. So I think that longevity can learn from this. Yeah. When it comes to the other thing, yes, I agree. What I've presented here is where chain ladder is working, and is digging into that. And as also was mentioned before, situation like that, then we need to take other more dramatic means to solve the problem. I've worked, as was told, with a book on quantitative operational risk estimation, and that was the question similar, that you have to get prior knowledge into statistics. And for me, it's the same you're talking about. You need to combine statistical models with a lot of insight and had to put them together, which is not really statistics. It's a combination of statistics and something else, and this is the challenge as I see it. Yeah.
Can I ask you, Jens, then about validation? It's a big theme in actuarial work at the moment with Solvency II coming along. Everything has to be validated in a manner in which it wasn't formally validated before, both internal models and technical provisions. Technical provisions obviously playing to this reserving question. So is there anything else you can tell us about validation? If someone were externally validating it, for example, what would they ask for and what would they see?
Oh, sorry, I didn't get the last question.
If you had an external, all the validation that we've spoken about so far has been done by the practitioner who's coming up with the numbers, and he or she takes off the last diagonal or some other set of points and sees what happens. How would you envisage validation being done by or directed by someone external to the process?
Without access to the data?
Yes, perhaps. That would be even more interesting. Because I read for those of us who don't want to get out.
I'll get back to. I'm trying to win time. Right? But before that, I'll say, when it comes to validation, then the validation presented here is what you can do with the kind of data we are having at the moment. Obviously, if you have the original granular data, you can do more. You can split the data in two and validate one against the other and do all kinds of things. So really having the original granular data is helping you a lot when you do validation, no doubt about it. So no matter what I said in the introduction and so on and so forth, being able to split data sets and validate one against each other is very important when it comes to validation. Doing an external validation without access to data, that's a good one. Yeah, I will think about it. Yeah.
Martin White again. This isn't a curveball for Jens at all. This is really in response to what David Wilkie was talking about. In other words, where you have a claim situation that is not the product of lots of little things happening in a pattern. When I came to the London market, I was privileged to get about half a day of David Craighead's time, and he showed me through the numbers of some of his clients who'd okayed it. And he was reserving for things like reinsurance and retrocession accounts where there'd been a catastrophe. And he was looking at individual years and finding that they all developed very differently from each other. And he had ways of fitting formulae that seemed to make sense. And they more or less worked. But the key point was that years were not different, and you had to have some insight as to how losses would flow around the market to make a guess as to how big they'd ultimately be.
It remains for me to express my own thanks, and thanks of all of us to the speaker, Professor Jens Nielson, and also to all those who participated in the evening's discussion. Details of upcoming events are available on the Institute and Faculty of Actuaries websites. And in a moment, when I declare this meeting closed, you can turn on your mobile phones and Blackberries again. But before we do that, I would like us to show our appreciation, particularly to Jens Nielson, in the usual fashion.